This is the first video in section 3.2 on limits and continuity. The goal of the section is to understand the similarities and the differences between the limit of a function of one variable and the limit of a function of several variables, and to state the condition for continuity of a function of several variables. In this section, we're concentrating on a function of two variables, z is equal to f of xy, but the definitions and concepts we'll see here have immediate analogs for functions of more variables. So let's start section 3.2.1 on limits. We'll begin the section by establishing the analogous intuitive definition of a limit and evaluation method that you probably saw for functions of one variable in your first calculus course. Definition 3.2.1, the intuitive definition of a limit. Let f be a function of two variables whose domain includes a small disk around a point AB. We'll talk about a disk in just a second. Then we say that the limit of f of xy as xy approaches AB equals L, and we write a limit notation that you're very familiar with, except it's not just x going to a point A now, but xy going to AB. We write this if we can make z of f of xy as close to the value L as we like, arbitrarily close, by taking xy in a sufficiently small disk around AB. So let's talk about a disk. A disk is the plane equivalent to an interval on the real line. So for example, in 2 dimensions, given a point A, to evaluate the limit as x goes to A of a function, you need the function to be defined in some interval around A. And then you're examining what happens to the function in that interval, but not necessarily at A. So in 3 dimensions, when our domain is a point AB, so we're considering that point as being a point down in the xy plane. So really, as we've said before, that's really the point AB0, but we're thinking of it in R2 as in the input space of the variables x and y. We're looking at what happens in a disk around that point, not just an interval, but a disk around that point, like a small circle. And then the same kind of thing, you are concerned in what happens in the function surface in and around that disk. So in particular, what happens directly at the point AB is not important. The function may or may not be defined at that given point, but what happens sort of close to that point is what the limit is investigating. When we take values in an interval around A, we can either be on the right or on the left of A. So as you might remember, you can take your values on the left, on the right, which means that you are approaching A on the left or on the right. But when we take values in a disk around AB, we can be anywhere in the disk. So those values can be anywhere in the disk, and in particular, as we approach AB, we can approach in infinitely many different ways. Proposition 3.2.1, the direct substitution property. If f is a polynomial or a rational function and AB is in the domain of f, then the limit as xy goes to AB of f of xy is just f of AB. Really, it is drawing on the fact that polynomials and rational functions are continuous. This is the property that we're going to see for continuity later on, but this is the analogous property to what you would have seen in your first calculus course. The first thing you try to do to evaluate a limit is you plug in the point of investigation. So Example 3.2.1 says evaluate the limit as xy goes to 2, 1 of x squared minus y squared over x squared plus y squared. So we try and plug it in. So x is 2, y is 1, so 2 squared minus y squared, 1 squared over 2 squared plus 1 squared gives me 4 minus 1 over 4 plus 1, or 3/5. And the direct substitution property essentially says if you plug it in and it works, then you've got your limit value. Now, of course, that's in the specific case that we have a polynomial and a rational function, which is exactly what we have here. But really, it's true for any continuous function. If your function is not continuous, when you plug in AB, you may end up by getting an infinite form or an indeterminate form. And some of the algebraic tricks that you learned in Calculus 1 may be of assistance in evaluating the limit. I say may because the algebra with two variables can be quite tricky, can be more difficult than the algebra with a single variable. In fact, it can be quite tricky without the formal definition of a limit, which we do not have. We've only seen the intuitive definition. Without the formal definition, it can be quite difficult to show that the limit of a given function exists in two variables. So we won't be doing a whole lot of that. In the next video, we are going to see a special case where it is quite easy to show that a limit does not exist in that particular kind of case.